fog computing, to me, is to build an end-to-end architecture to really do a couple of things. The very first thing is to distribute computing, communication, management, and other functions and resources supporting those functions closer to the users anywhere along this continuum from the cloud to the things. And then after you distributed the functions and resources, you do the second thing, that is to make use of them. And that includes managing them and secure them and pulling them together, orchestrate the resources in different places to support end-to-end applications. And they are important in the sense that they fill a technology gap and actually a range of critical technology gaps. And then they're going to disrupt the business models. They are going to give us new services that we can do that we cannot easily do before. And they're going to change the landscape of the information and communication technology industry. People are still thinking about Internet of Things in the old computing model alone, which means you compute far away in the cloud or on your devices. And that computing model is having a number of limitations that do not support many of the new requirements of the Internet of Things. So those new requirements include real-time processing, at the terminal and edge level, processing a lot of data, supporting a large number of very diverse devices and applications, and conserve network bandwidth, and also integrating the different types of applications and the different types of networking capabilities into a manageable and scalable and cost-effective way of doing things, and as opposed to isolated and siloed way of doing things. And the list goes on. So supporting those new and emerging requirements, you really need this new paradigm. And this new paradigm basically is the fog paradigm that brings the computing and other advanced capabilities closer to the users. IoT is only one example of where fog really is going to provide a critical role. Take another example, 5G. And in 5G, there are several very important requirements. First, very fast establishment of the radio control and also the connections between devices and a large number of them. AI, for example, generates a lot of data at the terminals and also on the network edge. And AI requires real-time processing of those data. And it doesn't make sense for all of the data to be shipped to a faraway cloud. Sometimes it's just impractical. Very often you can't satisfy the delay requirement by sending them too far away. And so you need local processing. And not only you need local processing, you need the capability to shift some of the functions between the local nodes, let's call them fog nodes, and cloud. That demands a seamless integration between the two of them. So some of the capability, some of the processing, you may want to put on local nodes, for example, because today you're limited by core network bandwidth. Or today, your processing in the local node is still scalable. You're handling a relatively small number of applications. Tomorrow, you're going to handle a much larger set of applications, and that will require you to deploy more local resources that could get into a situation where you need to study the trade-off between doing it over there or doing some of the capabilities in the back end, and realizing that in the future the core network capabilities will increase as well. So that requires the fog and cloud to seamlessly integrate so that you can dynamically balance where to do what processing. And that's one of the characteristics of fog computing, that is end-to-end architecture and a seamlessly integrated architecture.